I know. We've been working with volts. Volts is going to be joules per coulomb. Coulomb's the unit of charge. Joules is energy. So volts gives us like how much work we can do per charge. Whereas now we're working with amperes or amps. That gives us the charge that flows per second. So your time has to be in seconds. So if we want to calculate mass plated over time, and I have metal in here, but it doesn't have to be metal. It can be any element that you want to form. Like we formed iodine in the lab. We could figure out how much iodine would be formed, that type of thing. You're going to do amps times time in seconds, and that gives you coulombs. And then you're going to cancel coulombs with Faraday's constant per mole of electron. And then I have here 1 mole of metal, but that could be 1 mole of element. Blank moles of electrons. That's that number in the half reaction, the number of electrons in the half reaction that it takes to oxidize or reduce it. And then we can do molar mass, and that'll give us how many grams we could get in a given time. You could also do like liters at STP. You could do 22.4 up there. That would work as well. And then if we wanted to reverse the sequence, we could figure out how much time we would need to plate a certain amount of metal, how long we're going to have to hook it up for. So just remember that the amps is coulombs per second, and that'll help you with these two things.
Wait, where can 22?
Up here where it says molar mass, we could also find like volume of gas at STP or something like that if we wanted to. We're just doing like, we're kind of like doing stoichiometry with a little extra special something on there. Yes. All right, so let's try one. We're going to try each process once. So what mass of I2, this is just like your lab, can be produced in 1 hour with a current of 15 amps. So I'm going to be doing that first process. And what does my time unit need to be to work with amps? It needs to be seconds. How many seconds are in an hour?
3,600.
3,600. At least we know something. Okay, so I'm going to start with amps times time. Because amps times time gives us coulombs of charge. That's a 15, not a S. I know my 5s kind of look like S's. Oops. I don't want a joule. What am I thinking? Okay, so I get 54,000 coulombs. And now I'm just going to kind of do a stoichiometry process for that. Coulombs are going to cancel with Faraday's constant, because that's the number of coulombs of charge we get per mole of electrons. Cancel, cancel. Now I'm doing iodine. If we think about iodine being formed,
It would be two.
it would be 2. And you can get that right off the chart. We've got the 2 electrons. So we would say 2 moles of electrons per 1 mole of I2. And then to get mass, I would say 1 mole of I2. And since it's a diatomic element, I want to do 2 of them. Gives me 253.8 grams. So again, I'm just multiplying it all out. Multiply, divide. And I get 71 grams of I2 produced. In 1 hour with 15 amps, I can get 71 grams of iodine. That's quite a lot. Like we just ran it for a minute or something, and then the iodine kind of dissolved in the solution. All right, let's reverse it. How long? So how long is going to be what? Seconds. Will it take to plate out? So that means how much solid forms. 1 gram of nickel from aqueous Ni2 plus with a current of 100 amps. So we're going to start with a 1 gram. And I'm going to divide it by the molar mass, because I want to get to moles. Still kind of works out when in doubt, convert to moles. And once you have the moles, now you need to do the whole electron and coulomb thing. So 1 mole of nickel is how many moles of electrons if we're using Ni2 plus?
2.
2 moles of electrons. And then we know that 1 mole of electron will give us 96,485 coulombs of charge.
And that there will give us
A lot of coulombs. I'm going to round it to 2 significant figures, 3,300 coulombs. And then since we know that an amp is a coulomb per second, what's a second? A
33.
coulomb over amp. So I can do my 3,300 coulombs. It's actually better if you don't round to the very end, but divided by 100, 33 seconds. Which is pretty fast, but we're using a lot of amps. I don't really think that's a realistic amount of amps, but I wanted you to see what it was.